So intuitively, the reason you need two constants and why you need two initial conditions for a mass on a spring with friction makes some sense, but then the question is, how do I actually solve for C1 and C2? I just kind of gave you the answer before. So I've rearranged things a little, and I'm actually going to solve for C1 and C2 now for a little more space. And the way you solve for them is usually quite tedious. You plug in t equals 0, and then z at time t equals 0 is negative 0.3. So I have z at 0 has to equal, okay, well, it's c1 e to the, it's negative 0.5 times 0 times sine of 3.16188 times 0 plus c2 e to the negative 0.5 times 0 times cosine of 3.16188 times 0. But that simplifies quite a lot. It was nice that the initial time is 0. So z of 0, we know, is actually supposed to equal negative 0.3. So I can replace the left-hand side here with negative 0.3. Then over here, e to the, this ends up being 0. E to the 0 is 1. So I have c1 times 1 times, I get sine of 0. Sine of 0 is 0. So this whole term actually just disappears. And then we've got plus c2. We get e to the 0 here again, so that's just 1. And then here we have times cosine of 0. Cosine of 0 is 1. So this whole thing just simplifies to c2. And that's actually how we get the first constant solved for. We have negative 0.3 equals c2. Which is what we had when I wrote down the whole thing in gory detail down here. All right, so that handles C2. What about C1? Well, we haven't used the other initial condition yet, so we're going to go ahead and use that. So we have z prime of 0 equals 1, and this is the part that kind of sucks. We have to take the derivative of this whole thing. All right, so here we go. So we have z prime of t equals, all right, so we have a product rule and a product rule. We have a constant. So we're going to have negative 0.3, sorry, C2 we solved for. So we have C1 still, and times, so let's take the derivative of this first. We have negative 0.5 from the derivative of the exponential, and then e to the negative 0.5t times sine of 3.16188 t plus the derivative of sine is positive cosine, and it's going to pop out a 3.16188 in front. So we get 3.16188 times e to the negative 0.5t times cosine of 3.16188t. All right. So that's the C1, and then we have our minus 0. And I'm going to have to do this on the next line, minus 0.3, that's the C2 that we solved for previously, and again we have another product rule. So I'm going to do the e first, so I get negative 0.5 e to the negative 0.5t times cosine of 3.16188 t, and then I have the cosine, so then I take the derivative the other way, so I have e to the negative 0.5t, that's going to stay in this part of the product rule. The derivative of cosine is negative sine, and because this is a chain rule, it's going to pop out the 3.16188. So I end up with a minus 3.16188 e to the negative 0.5t times sine of 3.16188t, close parenthesis, then bigger parenthesis. All right, so in order to actually, that sucked, but now we actually have to plug in z prime at time t equals 0, and that has to equal 1. So we have z prime at time 0, well, we can plug in t equals 0 everywhere. So we still have a c1, I'm going to have to do this a little here. So we have negative 0.5 times e to the 0, so that's a 1. Then we also have sine of 0. So actually this whole first term in the parentheses disappears, it's just a 0. And then I have a plus, so we have 3.16188 e to the negative 0.5t, e to the 0, because we're plugging in t equals 0. And also we get cosine of 0. So we get 3.16188 times 1 times 1. So we get plus 3.16188. Then we have our minus 0.3, and we have the stuff in here. So we have this negative 0.5, we have e to the negative 0.5 times 0, so that's just going to be a 1. Then we have cosine of 0, that's just a 1. So the whole thing turns into negative 0.5. So the first piece is minus 0.5. And then the next piece, we have minus 3.16188 e to the negative 0, so that's a 1. But then we also get sine of 0, because t is 0. Sine of 0 is 0, so this whole term actually just goes away. So it's just a minus 0. And so we have now this expression. We have c1 times a number minus 0.3 times some numbers. Let me simplify a little bit. So that's equal to 3.16188 c1. We have a minus 0.3 times a minus 0.5. I think that's positive 0.15. And we also know that z prime at time t equals 0 has to equal 1. So we can put a 1 right there. So now using this, we can actually solve for c1. And it turns out, I'm not going to do all the algebra here, right? So you would subtract the 0.15 over, that'd be 0.85. You divide 0.85 by this terrible number, 3.16188. That would give you c1. And so supposedly that number is 0.31523, approximately. And so that gives you c1 equals 0.311523. And now that you have c1 and c2, you're actually done. You now took the general solution. You solved for c1 and c2 by plugging in the initial conditions. Unfortunately, this z prime one was painful because we actually had to take the derivative of our solution. But at the end of the problem, we were able to come up with the solution that solves the ordinary differential equation and satisfies both of these initial conditions. Unfortunately, this is pretty common for the numbers to get ugly. They aren't always integers or fractions. But that's how you do it. To get your general solution, you evaluate it at each initial condition, and then based on that, you usually can find C1 and C2. And sometimes you even have to solve simultaneous equations. Sometimes you get the first initial condition will have, negative 0.3 is some number times C1 plus some number times C2. And then this other one will come up with some different number equals some different number times C1 plus some different number times C2. You actually have to solve a system of equations to get C1 and C2. But that's the idea, and intuitively I hope you understand why we have as many initial conditions as we need from kind of the physics examples, and also how to solve for them. And you'll be solving for these initial value problems quite a lot, so you'll get a lot of practice.